Good afternoon. My name is Ed Morris, and I'll be speaking today on a 3-year line project called Video Summarization and Search. I've also asked Adam Harley of CMU to discuss his contributions to the work. The problem we're trying to address is that aerial surveillance demands full attention of small teams called tactical PED teams with 3 to 5 people. They are on the job 8 hours a day and 3 shifts per day, obviously, to fill the 24-hour period. It's a manual process. It's error-prone. Analysts get distracted. They may be focused on the wrong areas, and many other things can happen. In addition, the changeover between shifts is very problematic. There are also technical barriers to providing good tooling for them. Our technologies for object detection are not as good as they should be. Once we detect an object, we can't recognize it consistently as the correct object, and finally tracking those objects is very hard. These limitations result in poor pattern recognition in a surveilled region. And of course, pattern recognition is what they really need to do. They don't need help necessarily identifying things as much as they want to find the bigger patterns. Our approach is twofold. We're working with DoD in pattern recognition technology for aerial surveillance data. And second, we're working with CMU researchers to address core technology problems associated with object tracking. We have several achievements to date. First, we've been influential in DoD pattern detection strategy, and we're currently serving as a reasoning pathfinder for DoD. Reasoning is their word for pattern detection or pattern of life detection. Our 3D tracking research is also achieving state-of-the-art performance. Our products are source code that's primarily available to DoD, and also publications that are in the public literature. Once again, we're currently involved in 2 activities. First is support to DoD, and second is the research. In terms of transition, we're doing several things to make the DoD capability for tracking better. First, we're removing dirty data from the aerial camera data. There is a lot of dirty data in camera data. First, the values of the onboard sensors for lat and long could be incorrect. And second, the platform drift itself often leads to spurious detections or missing detections, and it certainly leads to bad downstream tracking, and for other apps as well. Our approach then is to clean and smooth the data prior to downstream processing. First, we can apply moving median smoothing techniques to kind of get rid of the unrealistic jumps in speed and location that occur in the data streams from these platforms. Second, we can correct some bad geo-registration locations. The 2 images on the right show an example of that, where the blue boxes are fixed and we know where they are. The red boxes initially on the image on the left are the lat-long location that is given to us at least at one point for those 2 boxes. The reality is in black. And after our geo-registration strategies, we have now located them in the correct spot. Third, we can apply Kalman filtering to reconnect tracks that have been dropped or correct tracks that have been switched. We can also improve lat-long with that strategy. A second thing we're doing for DoD is statistical reasoning about this aerial surveillance data. Keep in mind that most activity is normal and not harmful at all, but some of it is. We can use our statistical pattern of life detection capability to map out what's normal in terms of a location that's being surveilled, detect anomalous activities that potentially could be bad, and ultimately search for those activities in a data stream. The implementation is pretty straightforward. We separate the region into grid points based on camera attention. We remove the bad tracks. We calculate things like mean speed and heading and density within that data, and then we can detect anomalies based on a set of rules we set for what is considered inappropriate speed or inappropriate heading. The examples on the right show that. The top example would be what the tracks look like coming out of the data. The example on the bottom shows what happens after we do our statistical reasoning, where we now have identified things that are moving fast, obviously on a roadway, and things that are moving slow. A third thing we're doing is we're applying anomaly detection, machine learning-based anomaly detection strategies. What this basically is applying an LSTM, or long short-term memory autoencoder, to observe a set of tracks. From that observation, it begins to understand what's normal, effectively. Now, when you provide other tracks to it, it will say, well, if it can reconstruct those tracks based on what it knows, it considers it normal. But if it can't reconstruct those tracks, in other words, there's a high reconstruction error, then they're identified as anomalous. The image on the right shows an example of this in action. This data was actually perfect data coming from GPS devices in cars for a DoD exercise. On the left, in the green, with the green dots, those are presumably individual cars on a roadway. The tracks are not shown here, by the way. That's a perfectly normal pattern of activity. However, the anomaly detector was also able to detect two vehicles that met on a little-used road in this exercise. Now, whether that's important or not, of course, depends on the mission. And I want to point out again that this was perfect data. This is not necessarily what you would see with an anomaly detector applied to the tracking capability we have now. So what are the barriers to progress? Well, poor object tracking, which I've talked about, is certainly one of them. And there are several reasons for this poor performance of object tracking. First, the current state-of-the-art in object tracking uses 2D camera frames and then identifies objects across frames and relates them. Well, the problem, of course, is that objects look different depending on the viewpoint. A car from the front looks very different than a car from the back, so it's very easy to throw off the object detector and recognizers. Second, any kind of occlusion throws off 2D tracking techniques quite a bit. Even partial occlusion, going under an overpass or being hid behind a tree, can throw a tracker off significantly. Third, the coordinates in the frame are not necessarily good enough for you to predict where that object will be in the next instance. The example on the right will show this. I'm going to start up this video now, and you can see that the people walking are, even though we know they're walking a straight path, their location within the frame is not what we would expect based on a straight path. It's actually moving based on camera motion. There's a secondary problem too, and that is the best performing tracking algorithms require many images in order to train to detect those objects. But the reality of DoD is you often have very few images. For example, if there's a new missile launcher platform that an adversary has deployed, we are unlikely to have a lot of images of it. We may have some. We're very unlikely to have enough images of it from various perspectives to be able to recognize it in many different situations. In addition, there are many cases where analysts are looking at the images or the video coming in, and they may not know what the object is, but they do want to track it. So you need to have a capability that allows you to do that. The result is, once again, poor identification of objects, lost tracks, and poor pattern detection. Our strategy for addressing that is we're collaborating with Adam Harley and Dr. Katerina Fregiadaki from the CMU campus. Adam has done a fantastic job and has turned this work into the focus of his PhD thesis, and I'm going to let him take over at this point. Thank you, Adam.
Thank you, Ed, for the introduction. Before I get into the work itself, I'd like to motivate it a little bit more with the help of these videos. So what we want to be able to do is take a video like this one as input. This is a video captured by a drone looking down at the ground, and we want to be able to produce as output detections for all of the objects of interest and also tracklets for those things, which just means drawing on a map where we think those objects moved over time. And we're going to be talking about models that do this with the help of 3D information. And it's useful to say why we care about 3D. And one of those reasons is that it actually makes the job easier, meaning it makes detection and tracking easier. One way that it does that is by stabilizing the data. And so, for example, here, stuff that was stable in the world is now suddenly stable in the video. And that's a nice thing because it can make things that were initially complex into things that are now very straightforward. Like this trajectory over here, for example, while it was a little unpredictable in the original video, after you take into account the camera motion and sort of cancel it out, then suddenly it's just a straight line, and it's a person walking along a fence. So the hope is that if you take into account the 3D geometry of your domain before asking a machine learning model to do any learning, then that model is going to generalize better than one that has to figure out the geometry and the problem of detection and tracking all at once. For the results I'm going to show today, it's mostly going to be on urban scenes like this, because that's the data that we have in academia. But in general, the same kind of method would work no matter where your camera is, because everything is 3D. So there are going to be 3 parts to my talk. First one is about tracking objects. The second one is going to be about tracking the camera itself, so that you can do the kind of stabilization that I was talking about. And the last part is on a model that proposes things that are worth tracking. And then the hope is that all 3 of these can sort of work together so that you propose objects to track, track them, and also improve the tracking or make the tracking easier by canceling out the camera motion. So for tracking objects, the main problem that we wanted to address is the amount of training data that you typically need to train a good tracker. So tracking labels are very expensive to obtain in the real world, and if we can reduce the amount of labels that you need, that's a good thing. So we tried to think of what are some other labels that might work just as well. And what we came upon is this idea of static point correspondences. So here I've got 2 frames of a video, and I've marked a couple correspondences. So for example, this little pixel over here is on a sign on a fence, and I can find that same pixel down here. If your whole scene is static, meaning nothing is moving except for the camera, then it's fairly easy to solve this these days. Like, you can just download an algorithm off the internet and produce tons of these correspondences. So what we thought is that it would be nice to use these correspondences from static points to be able to learn how to track moving objects. And the key insight, you could say, is that the features of these stationary parts of the world are going to be pretty similar to the features of moving parts. So all we need is something that can do the correspondences visually rather than rely on geometry, which is what the classic algorithms would rely on. So as output, you end up with something like this, where I've got the ground truth shown in yellow and the estimated boxes in blue, and accuracy is shown in the numbers. Also, to explain a little more, so this view up here is the camera's viewpoint, and this is a bird's eye view down here. Mostly this is successful, which is kind of incredible since we're not using any tracking labels. It's just those point correspondences. The boxes do jump around a little bit, but this is maybe understandable because we don't have any motion priors right now. All we're relying on is these frame-to-frame point correspondences. And we're able to show that this works not only in a simulator, but also in real-world videos. Quantitatively, it looks good also. So in this plot, I have all of the supervised models, or sorry, the self-supervised models are in solid lines. So ours is in black up here, and it's a good margin above the rest. The supervised models are in these dashed lines. And you can see that in the harder data sets, especially as you track for a longer period of time, you are better off using a supervised model, but we're not too far off. So the main idea here is that we show that if you learn correspondence from static 3D points, then 3D object tracking will emerge. The second thing is, in the paper that corresponds to this, we're also introducing a neural 3D mapping module, which is just our 3D neural network. And this simplifies prior works trying to do similar things for 3D inverse graphics. We also, in this paper, introduced a method for training for correspondence in dynamic scenes, which people haven't been able to do before. And our method here is very simple. All we do is, if a video has dynamic parts in it, we manage to just discard those moving parts and only train on the static portions. And it turns out this is an important thing to be able to do, to be able to train on real videos. So that's part one, about tracking objects. And here I'm going to talk about tracking the camera itself. So our method for tracking the camera is actually pretty similar to how we track for objects, in terms of we're going to have something from some reference, which in this case is going to be our map that we're building over time. And then we have some new input that we want to localize with respect to the reference. And we specifically turn our map into a 3D feature tensor, similar to before. And we also turn the current frame into a 3D feature tensor. And then we do our cross correlation. So this is, as before, just doing a lot of dot products at different spatial positions. And then we turn this into a rigid transform, just like for object tracking. But in this time, we're doing all of this in a loop, so that we're able to add to the map and make it more and more dense over time. and that makes this model into a recurrent thing. So overall, just to have a clean takeaway, we're taking as input RGBD videos here and producing as output the rotation and translation of the camera as it goes through the scene. So I've got qualitative results here. This is the RGB of the video going into the model. And here on the bottom is the map that is building over time. So you can see that this map is getting denser and more complete. And also you can see that the red trajectory is our model's estimate and the green trajectory is the true one. And these are pretty close together. This is an important step for us because we want to be able to always localize the camera with respect to a map, and we want to use that to be able to stabilize videos, like I showed at the very start. But quantitatively, it turns out we're still actually far from the traditional methods in this domain. So we're able to show that the things that we're adding in terms of map building and this course-defined refinement, they do help us reduce our error, but OrbSlam 2 stereo is just a phenomenal method. So we're still trying to beat that. In general, though, we're working here on a neural Egomotion module in terms of, Egomotion, I just mean camera tracking. And this is capable of map building, which is kind of a unique thing for a neural network. And gradually we're closing the gap between the deep and so-called traditional methods by essentially doing what those traditional methods are doing, but in a neural model. So we're hoping that this is going to pave the way for a more general system that is maybe more closely linking the two, and it's also going to work in the domains where the handcrafted methods fail. What I want to show here is a method that can propose objects and then track them all on its own. So no human intervention at all, just deploy this thing and it's going to find things and start tracking them without any supervision or intervention. So this is useful for if you don't have good detectors for the thing you want to track, or also if you want to be able to track without a human in the loop. So here I've shown on the left the input to the model, which is going to be an RGBD video stream. And similar to before, we're going to be creating 3D estimates of the scenes depicted in these frames. So I've shown these volumes here, and again, inside each inside each cell of the volume, we have a vector that encodes some semantic content. The key operation here is a median followed by a subtraction. So first of all, when you take a median of all of these volumes, a median over time, you end up with an estimate of the stable part of the scene, which corresponds to the background. And then when you take a difference from that median, you end up with an estimate of what's not background. And in other words, that's going to be mostly your objects. I can show already what that looks like. So given this video on top, the median is over here. You can see it's perfectly stationary because we take one median, no matter how long the video is. And down here, I've got the differences from the median. And what you should see here is, in a bird's eye view, we've got a bike over here and a car coming down, coming from the bottom. So the important thing is that the big white blobs in the bottom here in the difference map correspond to actual objects in the video. And we have a process also that's able to select these blobs and sort of sort them big to small, and then start to track them. And essentially we just use the method I showed in the first part of the talk to be able to do that tracking. So in this bottom right column, bottom right part of the slide, I'm showing what those tracklets look like. So it's really that simple. Given an RGBD video, we find 3D median and then take differences against the median, and that's your objects. So we've shown that object discovery is surprisingly easy if you appropriately exploit the geometry of the scene, and also, of course, if you have access to high quality information about like depth and camera motion. And the nice thing about this compared to previous object discovery methods, like ones that try to do discovery based on optical flow, for example, is that here we're using very long time horizons, which seems to be much more reliable signal than these short time horizons. So that's all from me. Thank you.
Thank you, Adam. Just to briefly summarize, we offer transition support of the work we're doing to DoD, and in addition, we support research on 3D tracking. Our next steps are to continue to work with the DoD to improve pattern recognition for aerial surveillance data, and of course to continue the 3D tracking work of Adam Harley and the CMU team. Thank you all very much. Are there any questions?
Good afternoon. I want to thank each and every one of you for attending the research review, and in particular this session. I'd like to start out with a question for Adam. Adam, what are the major advantages and disadvantages of your approach compared to other approaches that are based on trained object detectors?
That's a great question. I think that the main disadvantage of using a pre-trained object detector is that there's a built-in assumption that that detector is going to work when you try it on your test set. And that's a tricky assumption to make because you don't really know how different your training distribution is going to be from your test distribution. So what my approach is trying to do is get rid of that assumption by allowing us to do some self-supervision in the test domain. So if you're able to improve your trackers, improve your detectors just by using free labels that you can acquire from like multi-view data or optical flow, something like that, then I think you're more likely to do better on the test set. So the main benefit really is generalization, I think, from my approach compared to using some pre-trained object detector. Maybe I can ask you a question, Ed.
Sure.
What more is needed to make a more sophisticated pattern recognition system possible for aerial perspective systems?
Wow, a whole lot, actually. First, we need more and better object detectors, as you could expect. Right now, we're at the point where we're doing the fried chicken situation. We're in the fried chicken situation where our current object detectors can sometimes detect things like, or classify things like explosions as fried chicken. And that's the reality, even for large objects from aerial perspectives. We also need to understand much better who the people are that we're seeing down below, if we're seeing those people to start with. It's not enough to say there's a person down there, but we have to know whether that person is a man, woman, or child. We also have to know whether that person is armed or not. So once we do that, there's still a lot of work to determine what particular weapons or other supplies are available on the ground. Now, that's just the detection of the objects themselves, but the bigger problems or the bigger benefit actually comes later on when we can actually detect patterns. For example, you can imagine a situation where there are barrels of what look like to be industrial chemicals, there are agricultural products, and there are fires burning. Well, that represents a pattern that may be the processing of drugs. Or the creation of heroin from poppies. Another situation where there are unusual delivery of crates at various and unusual hours, specifically sized crates, and it may be patrolled, the area may be patrolled by armed men. In that case, it may be a weapons cache or something like that. And that's the type of the pattern over the longer term we have to be able to understand. But there's more still. It's not just that we recognize those patterns in an instant, but those patterns appear over time. The crates can be delivered one day. The armed guards appear later. And in terms of the barrels, they may be delivered one day if it's a drug processing situation. So the point is we need a history of those things, and we have to recognize the pattern occurring over that period of time. And that period of time could be quite long, actually. So once we get beyond the point of the history, there's still the relationships to other forms of intelligence. So, for example, we may want to know, it may be very useful for our focus of our pattern detection to know that an informant, for example, suggests that there's some activity going on in a specific area, or that a number of armed unknown men have appeared in a particular area. So all of those things are important to know, and we're not nearly there yet. To kind of close, the value of all of this work will come down the road. It's not going to be immediate, but there is a lot of work that has to be accomplished before we get there. Thank you all very much. I appreciate the time that you've given us this afternoon. Thank you.